On polarity or intermolecular forces or anything else?
It's hard.
For what?
It's hard to bring to write down those polarity molecule. Needs more energy compared to polarity. Always attracting electron.
Always what?
Always attracting electron, or there is sometimes polarity.
Repels?
All of them the same, the polarity. Like
No.
polarity means holding electron.
Well, polarity means it has one side is more positive, one side is more negative. So one side of the molecule is accepting electrons a little bit more than the other, more electronegative. I'm not sure.
Another side is positive, doesn't it?
What?
Another side is positive, full.
It's partially positive. It's not. So if you drink water, do you get shocked?
A little bit.
Do you? I don't. But so it's not charged. It's just not sharing the electrons equally. That's yeah. And so if you get a stream of water and you get a balloon and rub it on your head and you put it next to the stream of water, it will deflect it because water is polar.
It's hard to break it.
It won't break the molecule.
Yeah, or it's
It
more attracting.
so polarity doesn't tell. Well, kind of is related to the intermolecular forces, but I don't know if I'd think of it that way though. Good. Anything else? Yeah, Chad.
These are questions just in general.
Yeah.
I had a question from the master in chemistry.
Uh-huh. How it's not grading, putting on your grade?
No, it wasn't
I
that.
think I fixed that problem. So check in the next day or so.
A specific question.
Okay. Yeah. You're good. Does anybody else have any questions while we're waiting? Andrew.
I had one on that as well. I could not, like zinc phosphate, like writing the formula, just stuck.
Oh, so how you come up with? So how do you write this formula? Is that what you're trying to do?
Yeah, I guess so. Yeah.
All right. So zinc. Well, I just did it, but now how do you get that, right? So it says zinc phosphate. So we know zinc is a metal, and phosphate is a what?
Phosphate is a gas.
Polyatomic ion, right? So we look at our polyatomic ion list, and this is PO4, 3 minus, or we just look in our brain because we need to know that, right? Okay? And zinc is a transition metal, so how are we going to know its charge, right? And it's not called zinc 2 phosphate, right? Zinc is one of those exceptions. Did we talk about exceptions in here? I won't test you on these, but in mastering chemistry, they're most chemistry classes teach it. Okay. So let me pull up a periodic table. All right, the exceptions are these three right here. And of course, these two right here. Did we talk about these two? So all of the transition metals are variable cations, right? They have different charges. So you can't look at the periodic table and know what their charge is, or know how many valence electrons they have, for example, okay? Or how much they will lose, or how many they will lose, right? Silver, zinc, and cadmium, they only have one ion form. Why is that? I don't know, it just is. Just what we found, okay? And so here's the way I remember it. Well, silver is in group 1,1. 1 at the end means it has a charge of 1 plus. And zinc and cadmium are in group 1, 2. And this isn't why, guys. This is just helps me to remember why. And that's those two elements have a 2 plus charge as an ion. And so we know that zinc is a 2 plus ion. And you cross the charges and simplify. Well, what about tin and lead? They're also variable cations. They act like the transition metals. What?
They have 4.
Not always. Well, they have 4 valence electrons. They do. But they are variable cations. So it's not always going to be +4.
Sometimes they
It could be +8 sometimes. +6. Do you have to memorize what it is? No. Just know that they're variable just like the rest of the transition metals.
They said zinc 3, it means 3 of
Zinc 2 plus.
No, 3 over here.
Oh, right here? It means there's 3 zincs. Uh-huh.
Yeah.
How do we know that? Because the 3 goes down here and the 2 goes down here, right?
Yes.
Yeah.
And cross multiplication to be
Well, we don't multiply, we just cross them down. Uh-huh.
6 and then
Yeah.
get
Chad?
So does tungsten, for example, have 6 valence electrons?
No.
So for the transition metals, what do the top numbers mean? The 3?
Means it's the group.
It's just the group.
Now, even over here, this doesn't mean 1 valence electron. It doesn't mean that. But we just use the periodic table to help us to remember that. That's it.
I see.
Okay. Now, why are all these guys 1 plus ions? Because the closest noble gas has 1 less than it, so it has to lose 1. That's why.
Okay, and I have my question.
Okay. Did I answer your question? Okay.
Another question. So I think on part of the homework it was like carbon with chloride, and then it had like a 3, and it was like you had to guess the actual one. I was able to get through it, but my question on carbon,
So,
I know on the notes
can
carbon.
I stop you just for a second? Sorry about that. Can we answer Chad's first?
Oh, yeah.
Sorry.
I think it might be the same.
Oh, is it the same one?
I thought you answered his, so I.
Okay. Sorry about that.
I think it's the same section because, yeah, it asks like, the following formulas are unlikely to be correct. Propose the correct, more likely formula for each of the following.
Okay, so give me an example.
So the video helped somewhat, but I struggled with N2H5, and it wants you to propose the correct chemical formula.
Okay.
But the carbon one was one of those, and I also looked at that one.
What one's the carbon one?
It's C and then Cl, I think 3.
Okay. So this has to do with the octet rule. Okay, so this goes a little deeper than what I'll test you on, but it's good to know anyway. Okay, this just gives you a problem where you have to think about the octet rule. We need to know the octet rule. I probably won't give you an example like this on the test, but it's good to know it. So let's go look at it. If we draw the Lewis structure here, how many valence electrons does nitrogen have? 5. Multiply that by 2. And hydrogen has 1. Multiply that by 5. And we got a total of 15. If we have an odd number, it's not going to happen. Well, I shouldn't say it's not going to happen. In general, it doesn't happen. Okay? So if we're to draw this, 1, 2, 1, 2, 3. Two, 4, 6, 8, 10, 12. We have 3 left. Where are they going to go? Oh, maybe right there. Oh, but if we put it right there, hold on, we can't put it there. Maybe we'll put 2 right there. Now they all have an octet, but we have 1 more electron. Where are we going to put it? Everything's happy, right? So that probably won't happen. And this kind of helps us to predict if a compound really exists, for the most part. Okay, there's always exceptions, guys. So that one doesn't look great. So I don't know, what should we try? If we add another hydrogen, it's going to make 16. Then we have 2 extra electrons. Again, they all have an octet. But if we lose a hydrogen, then we have how many? 14. And there they are. 2, 4, 6, 8, 10, 12. No. 2, 4, 6, 8, 10, 12, 14. And now they all have octets, and we used all of them. Does that make sense?
So 2 lone, so a lone pair on each of the nitrogens.
Yeah. And that's okay, because how many electrons does nitrogen bring to the table? 5. And that still has 5. Hydrogen still has 1. So it's like they're just bringing their own, and right? It's like sometimes some will just, hey, oxygen will just take more, right? Than 6. But does that make sense?
So you're just pairing it the way of.
Well, like if you do this, there's the Lewis structure for, can y'all see this color? And then you have, so these guys share, and then hydrogens have 1. And they share all of these, right? And it works. No problem.
So NH4 and 2H4.
Yeah. And then you could do the same thing with this one. Carbon would just kind of have 1 extra electron around carbon in this one. So, okay, it needs 1 more bond. Carbon always bonds to 4 things. Well, I shouldn't say that, not always. Sometimes it has a double bond, right? But it needs 4 around, specifically around carbon. 2 of those could be on the same side and have a double bond. That's okay. But it has 4 bringing to the table. Carbon doesn't want more, doesn't want less. So what would be a better one? CCl4.
So would the better one for M2H5? Oh, you have it right there.
Yeah,
2H4.
Does that make sense?
Yeah.
And we don't talk about formal charges in this class, but that's basically what it is. Anything else? Did that answer your question too?
Yeah.
Okay, great. Yes, please bring your questions to class, because, I mean, I don't know how many times students say, I get it in class and then I go and I just don't understand, right? So bring your stuff to class. Anything else before we move on? Today we don't have a lot of stuff to go over before we're done with this unit. And then we will do review, or, so if you guys aren't ready for review today, we could probably just move on, actually.
We're going to
maybe I can't move on.
We will go study.
I could if we needed to. I didn't bring my notes for my other section yet. So, I mean, I could look it up and just remind myself what it is and then, and that's not a problem either. But if you guys have questions, I don't know if you guys went over the study guide. I told you can ask questions on Tuesday, and I'm not gonna go back on my word. If that's what you guys plan for, then I'll do that. But, you good? All right. Today we're going to talk about solids. So solids, we can have ionic solids, covalent solids, and a few other types of solids. So let's talk about these. So we got ionic solids. And all ionic compounds are what type of solids? Do you remember? It's a metal and a nonmetal. But what kind of solid is NaCl, for example?
Tables.
It's a salt. And if you were to describe a salt, how would you describe it? Not sweet. Looks like sugar, but it's not sweet, okay?
It's very acidic. Crystalline
solid, right? And that's how all ionic compounds are. They're crystalline solids. And these, we know the properties of salts, right, or ionic compounds. What are they? What? They're crystalline solids, okay. High or low melting points? High, extremely high, right? And why is that? Because what? Yeah, but more importantly, the intermolecular forces are strong, right? It has the strongest intermolecular force. They have the ion-ion, right? And so high melting points, high boiling points, right? They're conductive. They're all these properties because
Iron.
of that. Ion-ion intermolecular force. Remember that? What we talked about last time? Okay. And so if we draw this, we have, and I kind of started drawing this last time. Is it okay to flip it and write the anion first? Sure, this is a 3D object. It's going to move around, right? And so you have your intermolecular forces between these guys. And that's pretty strong intermolecular force because this isn't just partial positive and partial negative, right? It's a full positive and full negative. So they're pretty strong. And then we can come back here. Whoops, wrong color. So that's just one little cube, right, of salt. But really it just keeps going, right? So that's the structure of our solid. Very strong, very structured. Are we good? So it also makes them a little bit harder than a lot of the other solids. Now, there are some solids that are harder than salt for sure, right? Okay, and we'll talk about them. Any questions with ionic solids? Okay, the next one is covalence. Yeah, question?
What's the other example of ionic solid without salt?
Ionic solids are just salts. Different types of salts. I'm sure you've heard of Epsom salt or bath salts, right? A lot of different types of salts, but they're all salts, yeah.
Sorry, this is a bit of an aside.
Don't be sorry.
Different kinds of magnesium, like I know there's like bisglycinate, malate, whatever. Isn't it just one element? Are those different kinds of salts?
If it's just magnesium,
Okay,
then it's not a salt.
okay. I guess I'm just thinking of magnesium salts, but.
But yeah, magnesium salt, I think Epsom salt, is that a magnesium salt?
No, sorry.
I-
Is it?
I think it is. But yeah, if it's just metal, then it's not a salt. So that's a different type of solid we'll get to in a minute. Good? Thanks for asking. Yeah, do it. Okay, the next one is our covalent solids. And what are the properties of covalent compounds? They share, good. Lower melting points, right?
Covalent bonds are very
Can there be solids?
because of
Yeah, what's an example of a solid covalent compound?
chewing gum.
Chewing gum? Yeah. Sugar is a common one. That's a crystalline structure. So what makes sugar crystalline versus wax is not crystalline, right? Wax or butter, these are both covalent solids. What's the difference? Talked about it last time.
Electronegativity is higher. And crystalline.
Yeah, electronegativity difference is higher for crystalline. Therefore, it's what?
Shiny.
Polar, right? It's polar, therefore it has hydrogen bonding or dipole are a little bit stronger than what? London dispersion for wax. Does that make sense? So covalent compounds can have a kind of broad range of properties because of that. There's different types of intermolecular forces. That makes sense? So we said ionic compounds are hard, and covalent compounds are softer. Now, sugar is a little bit harder than wax, but it's still softer than salt, right? Does that make sense to everybody? Why they have the properties that they have? Because of polarity and intermolecular forces. Questions so far? Okay. Now let's go to the hardest solids. What are they? Who can tell me a very, very hard solid?
Metal.
Harder than that. Diamonds. Yeah. Okay. And we call these covalent network solids. Anybody know what diamond is made of?
Carbon.
Carbon. Right? It's just carbon. That's a non-metal, but it's only carbon. So what's holding these things together?
They are atoms.
A covalent bond. A bond is always stronger than an intermolecular force. Does that make sense? So we just have a bunch of carbons, and exactly how they are, they're probably in different shapes, but okay. Probably a tetrahedral shape. And you just pack these in together very tightly and you get a diamond. Another covalent network is graphite, like in your pencils. Right? It's not as hard. What does that mean? It's not
Hot.
as tightly compacted.
Okay.
Right? How do we get diamonds? A lot of pressure, right? What's the difference between diamonds and graphite? Density. Really? Okay. They're both carbon. You guys ever watch the old Superman with Christopher Reeves in it? How he goes to the coal yard and he takes a piece of coal and he crushes it and makes a diamond, gives it to Lois Lane, right? Could you do that? Yeah, we do that. Maybe not with coal, but we do that. We can make lab-grown diamonds, right? Back before we could do this, I thought I had to just be in the ground with a lot of pressure, and it just takes millions and millions of years. No, it doesn't. Okay. All right, so let's talk about some properties of covalent networks. They're very hard. Very high melting point. So these guys they're stronger in all aspects, okay? That is the strongest type of solid, strongest bonds, because they are bonds and not intermolecular forces. We good? Yeah, Chad.
So like the intermolecular forces that we described last time are determined by the type of bond, like ion to ion, hydrogen bonds.
Mm-hmm.
So how are bonds stronger than intermolecular forces in this case?
Because if we have, let's say we have water, this is the strongest covalent intermolecular force, right? So we have water. And when we boil or melt water, or melt ice, I should call it, okay? Do we break the hydrogen off from the oxygen? We do not. We just break those water molecules apart. So for example, when we boil water, the molecules, the intermolecular force is broken, and now they're far apart, and there's basically no intermolecular forces because they're gases now. I mean, there is an intermolecular force, but they have to be close. Kind of talked about it with Eric the other day, but like brazing, or when you heat like a brass rod and you braze it, it doesn't work unless those pieces that you're trying to braze together are extremely close together. As soon as you get far apart, because what's holding that brazing together is that intermolecular force. As soon as you get that far apart, it will not adhere. You got to have them close. So if you have gas particles, well, they're not going to really be attracted to one another because they're too far away. Does that make sense? And the last type are metal solids. These are also very strong, not quite as strong as diamond, for example. They might be stronger than graphite. They are. We can see we could break graphite pretty easily and break it apart pretty easily. Metal's a little bit stronger than that. So metals have high melting points. What do you think compared to ionic? Higher or lower than ionic? Higher, right? Metals take more energy to melt them, okay? What kind of bond do we have for metals? Not covalent because they're metals, right? Metals are a little bit unique here. So if we have a solid piece of metal, that metal has protons in it, yeah? This is not drawn to scale. And those protons are kind of fixed where they are. But the electrons can move around. We call it a sea of electrons. This is what gives the metals the conductivity ability, right? They're the property of conductivity, because it allows those electrons to flow, be where they need to be. So if we have, for example, a rod, and this rod is, let's say, a plastic rod, and we charge it, so it's positive on one end. Where do the electrons go that are in this metal? They attract to that positive rod, right? Positive and negatives attract. You with me? If we were to get another rod and make it negative, what would happen to those electrons? They'd fly to the other side. Okay? So these are held together by, so if this is copper, it'd be copper-copper bond. But they're, yeah, it's not, yeah. Anyway, it's structured kind of like salt, but it's bonds. So that's why it's stronger. Make sense? And what allows them to be bonded together? This sea of electron model. Those electrons can move where they need to be for these things to bond together. Good? Yeah.
I'm sorry, I forget, does that make it non-polar or does that make it ionic?
It makes it metals. Yeah, it's a metal. It's not ionic. It's not covalent. It's a metal.
It's not covalent.
Yeah, it's a metal-metal bond caused by that sea of electrons. We call it a sea of electrons. It's not really a sea, but it's where the electrons can flow. And what electrons flow? Valence electrons, right? It's still the valence electrons that change. So it's not the inner electrons. They're probably not gonna move, right? But it's the ones on the outside that will move around. Good?
That's why, as you mentioned, we use it for transfer electricity.
Say that again?
It's only transfer electricity because of it.
Yeah. So again, it makes it conductive. I didn't put that on here. And it also gives it the property of being malleable or ductile. Okay, any questions on solids? That's all there is on solids. So what are you going to be asked on the test? Probably something about covalent networks, diamonds, graphite. And what do you need to know about these?
Just diamond.
They have the highest melting point, very high. They're the hardest.
Highest
They're the
one.
strongest bonds. Yeah.
There's any order like in those four, like which one is the like less strong and which is the
Yeah.
more strong?
So we would do, let's put these in order, good. So we got covalent solids are the weakest, or the lowest melting point, lowest boiling point, least strong bond. Then you have
Covalent solids weak.
ionic solids. Then you have metal solids. And then you have covalent networks. Great question.
Graphite is an example of a covalent network.
Yes, so that one might be somewhere over here. Right? There's all, but if we're talking about diamond, for example, right? That one's going to be the strongest of all. Okay. So, yeah, there's discrepancies, but
Also, it's
you don't need to know those. Just, yeah. Good?
covalent network is just diamond.
Diamond, that's good enough. Diamonds, yeah.
Diamond with high melting point.
Yep,
high price point too.
yeah. Good, anything else? So on the worksheet that you guys got last, was it 2 times ago? Or was it last time? Yeah, I gave it to you last time, right? So there's a table on the back. And if we understand this table, then I think that's really what we need to know. So we have solid type, and this is just kind of review what we just talked about. We have smallest unit. Intermolecular forces. And properties. And then some examples. Anybody need this worksheet?
Yes, yeah.
It's not a new one, it's one from last time. Okay? So we have ionic, we talked about. Maybe we can put these in order of, well, if you guys are just filling this out, I'll just do it this way, I guess. So we have ionic, the smallest particle of ionic solid is an ion, right? It's made of ions. You guys remember what an ion is, right? It's an atom that is charged, right? Intermolecular force is ion-ion. Kind of learned this last time. And properties we talked about. They're brittle, crystalline, high melting points, they dissolve in water. We talked about what happens when they dissolve, right? They dissociate. They break apart, right?
So
Yeah.
sodium chloride would break apart.
Uh-huh. And become Na plus and Cl minus. And that's why, that's why it dissolves, because what happens to the, did we talk about how things dissolve? We're gonna get there if we haven't. But we got sodium and chlorine, and we'll talk more about this later when we talk about water solutions. But what water surrounds it? What part of water surrounds it? The oxygen or the hydrogen?
Hydrogen,
Oxygen. Why is it the oxygen?
because it's negative.
Because it's partially negative. So the oxygen in water surrounds it, and that's why it dissociates, because it has water. There's a lot of different water molecules that kind of take over, right? What part of water surrounds chlorine? The hydrogen. More than what I'm drawing, but I'm just, keeping it simple. Good? And as soon as it's completely dissolved or completely surrounded, it's completely dissolved. We'll talk about this later, but what happens if you put more salt in it? You ever see salt that doesn't dissolve? Yeah, too much salt. That's because there's not enough water to completely surround every particle, right? And we'll talk about that later. And examples are just all ionic compounds, metal, non-metals, right? Has an ionic compound, if it has a polyatomic ion in it, it's also an ionic compound, right? So this is just review, kind of, ish. Are we good? Yeah.
How would that apply to what we learned last time where like dissolves like?
Uh-huh.
Because because water is polar covalent and salt is ionic.
Good. Remember this gal? What's over here? Ionic. Difference in electronegativity. So we don't call ionic compounds polar, but it's kind of it's just a really high polarity, right? It's not really polar. Well, they don't really share. They just say, give it to me, man, right? And one side has the electrons while the other doesn't, and they're electrically attracted. But same idea as polarity. Good? Great questions. So we can have sodium chloride, we can have ammonium hydroxide, and so on. Good? Thousands of different examples, but. Next, let's do the covalent or molecular. You guys understand those are the same kind of molecular solids? And the smallest particle of a covalent solid or a molecular solid is a molecule. Because the water doesn't separate, it just stays, that's the smallest particle of it. You with me? So there's 3 different types of intermolecular forces. What's the strongest? Hydrogen bonding, then dipole-dipole, and last is London dispersion. And if you need to write that whole name out, do it. And properties, they're softer, low melting points. They could be crystalline or amorphous. What does amorphous mean? It's softer, like wax or butter. Amorphous. Sorry. So we have wax, butter, water, sugar, oil. Doing okay so far? And then we have covalent networks. And the smallest particle is an atom, like a carbon atom, for example. And these don't really have intermolecular forces. So I was just going to write here covalent bond. And that's why they have the highest, because it's an actual bond. And I'll just say very high melting points. Very hard. Diamond is an example, which is just carbon. Well, it's not just carbon, it's pressurized carbon, right? And the last one, am I going too fast? Okay, the last one is metallic solids. And the smallest particle is still an atom, a metal atom, right? And how are they held together? Sea of electrons, right? So it's not a covalent bond, it's not an ionic bond, it's just the sea of electrons holding them together. The electrons can move so that they're electrically attracted. Okay? And that electric force is pretty strong force. There's only one, maybe two forces stronger than that. The nuclear strong force, you guys ever heard of that? What happens if you break that force? Atomic bomb, right? And another one, I don't know if it's stronger, but scientists have discovered another force out there, another, what do they call it? Universal force or whatever. It's the universe we knew was expanding for a lot of years, but we just recently, within the last 5 years anyway, discovered that the universe is not only expanding, it's accelerating. And according to physics, if you have something that accelerates, if this object is accelerating, how do I get this table to accelerate?
Force.
I got to push on it. Yeah, there's got to be a force. So there's another force. I don't know how strong it is compared to these other ones, but the electric force, what I'm getting at, is a very, very strong force. Compared to gravity, it's like 1 trillion times stronger. The electric force is. Well, you put a balloon, rub against your head, and you put it on the wall. Gravity's still pulling it down, but it stays there. And that's just a small charge, right? Our bodies are held together electrically, right? Every object is, okay? We good? So we know the properties of metals: malleable, ductile, conductive.
What's malleable mean?
Means you can shape it. You smack it with a hammer, it won't break, it'll just change shape. It's moldable, okay?
Long?
Conductive. To heat and electricity. They're also hard. Not as hard as diamonds, but they're hard. Like gold, iron, and so on.
Gold is himself is very soft.
It's a softer metal. Yeah.
And they
I
also,
think it's soft because on the TV shows you can bite, make sure it's.
they also make it very
good.
tiny for eating it or like decoration of the food.
Uh-huh.
They eat the gold.
That's expensive food. Yeah.
It's below gold.
Iron, sorry, just any metal.
Iron.
My bad. Tin, lead, whatever. Any questions on solids? All right, the very, very last part of this unit, I think, is probably a more straightforward part, hopefully. You do have to remember prefixes, but some of these are real common to us already. If they're not, then get them down. So let's talk about how to name covalent compounds. We call this covalent nomenclature. It's a funky word for how to name it, right? So when you get your homework assignment, I might call it covalent nomenclature. It's just naming it, okay? Naming or writing the chemical formula for it. All right, so let's learn prefixes first. The prefix that means one is mono. We didn't learn about this, right? Okay. Taught at my other class. I just couldn't remember which class it was that I taught. Okay. So mono, like monotone. You guys ever heard of a monotone singer?
Monotone.
Or maybe you have a brother or sister in a choir and they're just singing their part, right? You ever heard just one part? It's like, it's like, that's no good, right? But sometimes in a part, they just sing the same note over and over and over again. It's like, that's boring. But together, it makes everything beautiful, right? So monotone, the same tone. Mary had a little lamb, quit, 'cause that doesn't sound good. Okay, mono. That's why we use, okay, that's one. Two is die, like in dicycle. Yeah, I don't know why we use die, but we use die, okay? And three is, should know this one. Try, like triangle. Four is, it's not quad, it's tetra. We learned tetra, right? Tetra. Five is, like in a five-sided polygon is penta. Six-sided polygon is hexa. Seven-sided is not as common, but hepta. Eight is octa. Nine is nona. 10 is deca. Hepta. I'll be right back. Sorry.
How do you pronounce nine? No.
Any questions on the prefixes? So again, why are they this? Because somebody named them that way and it stuck. No reason. Well, there is a reason, but okay. But why is try 3? Because it's kind of like trace. I don't know. Trace, like in, I don't know. Probably, yeah. Yeah.
I think in like the decathlon,
Uh-huh.
I don't.
Yeah. Something like that. Okay. All right. Now let's get into naming. So to name covalent compounds, a little bit different than ionic. And what's our first step?
Make sure that's the right one.
Yeah, check to make sure what type of compound we're dealing with. If we're dealing with ionic, we do not ever use prefixes. Common mistake. In fact, I'm going to trick you today. Don't be tricked. Let's see if you get tricked. Do not use prefixes for ionic compounds. We'll see if I can trick you. Don't let me trick you on the test for sure, okay? I'm not trying to trick you on the test. I just need you to know the difference, okay? All right, so first step is determine type of compound. So if it's ionic, don't follow the rest of these steps, right? Use the steps we learned for ionic compounds, which are different depending on what type of ion we have, yeah? Okay. Step 2 is we name first element. We don't call it a cation, right? The first element in our compound with element name, or as element name. Name it
Element.
as the element name. Just like in ionic compounds for main group elements, right? Well, for covalent, they're all main group elements. So we're going to use this same rule, except for it's not a cation, right? It's the first element.
Third one.
And we're going to use correct prefix. If there's 3 of them, we're going to use what? Try. And so on. You with me? And another little note here. Don't use mono for the first element only. Just for the first element. The second element, yeah, we use it. Okay? Just to keep it simple, really. Step 3, name the second element. And just to this is binary covalent. What does binary mean? 2 of them, 2 elements. Just like when we talked about the main group ionic compounds, there's 2 elements in it, right? What about if it's more than 2? You take organic chemistry, and we have a whole different nomenclature for organic chemistry, okay? You guys always get those scam calls?
Yeah.
Holy, how do you get rid of those? Is there a way? Tell them that you died. I died. Don't call me anymore. All right. So name second element by changing ending to IDE. Same thing. That's nice. So just like in ionic compounds for main group elements, these are the same.
To ID.
To IDE. And don't forget to use correct prefix. But we can use mono for the second element.
Correct.
And that's it. That is it. Not too bad, right? For binary, not too bad. More than binary, whew, gets a little different. All right, so let's do some examples. Y'all have that? Okay. So, CO, who can tell me what that's called? Carbon monoxide. And some of us probably already knew that before this class, right?
Carbon.
Maybe.
Oxygen.
Okay. So carbon, we don't use prefix for carbon because there's only 1 of them. So we just say carbon. And then oxygen, how many oxygens are there? 1. So we're going to use mono, or we'll just say monoxide. We're not going to say monooxide. Why not? Because it looks like monoxide. That'd be goofy, right? So if there's two syllables, we just cut, or sorry, two vowels, we cut one of the vowels out, cut the right one out, just to make sure it sounds like the element name. Element name gets preference, right? Okay. And if we have CO2, what's that called? carbon dioxide. So in ionic compounds, if we have two elements bonded together, there's only one chemical formula you can write. One name for that, except for transition metals, and then we have to separate it with the Roman numeral, right? But with covalent compounds, there's several compounds with carbon and hydrogen in it, so we have to name them differently. Good? For example, we have CH4, C2H6, C3H8. This is methane. This is the organic name for it. This is the common name for it. But what is it called?
Carbon tetride.
Carbon tetrahydride. Use the same rules. Change the ending of hydrogen to IDE.
Metron.
So that's methane. That's the gas that we have in our furnace at home or our gas stove if we have a gas stove, right? Okay. So carbon. I'm not going to test you on methane though. You don't have to know it's called methane. Tetrahydride. And this is called ethane. And this is called propane. You guys, I'm sure you're familiar with propane.
Yeah, probably, yes.
Okay. So what's ethane? What's our name for ethane? Only if it's ethanol. So yeah. So if we put an O at the end, now it's ethanol. Okay. But this is what do we call C2H6?
Carbon
Dicarbon hexahydride. That's it.
Di.
You following? Why is it di? Because there's two. And the prefix we use for two is di.
It means they are dead.
Say that again, dicarbon hexa.
Yeah, so it's dicarbon hexahydride. Hydride.
Dicarbon.
Uh-huh. Do you have to memorize that? No, just memorize your prefixes. And if there's a 2 there, use di. If there's a 6 there, use hexa. That's it. And what's propane called besides propane? Tricarbon octahydride. Yeah. And I don't know if you guys are aware. You guys ever watch Batman? The bad guys putting poison in the water in Gotham City, right? Well, you guys know that they're doing that now. Do you know what they're putting in water? And it's not just a little bit. There is so much of it.
Chlorine.
What is it called again? It's dihydrogen monoxide. There's tons of it in there. Be careful.
Oh my gosh.
Dihydrogen monoxide. Well, that's the chemical name for water. Okay? I'm teasing. Okay. We good? Don't freak out, guys. You can still drink water, okay? I mean, there are additives in water, chloride and fluoride, whatever, but okay. We good? Can we name these? For the rest of the semester we can? All right. All right, let's do one more. Whoops.
What is the
What's that one called?
shape?
Everybody okay with that? Dipotassium monoxide? Anybody not okay with that one?
Dipotassium monoxide.
What kind of compound is this? Ionic. I tricked everybody. Ugh. Well, here's what's going to happen. This is the last thing on your mind. This is the last thing that I taught you. Now you go and take the exam. Say, oh, I got this down. I got the dies and tries and all this stuff. And then you use it for everything. So don't. Make sure you use it only for covalent compounds. Follow? That's why that first step is, what type of compound are we dealing with? Yeah,
So that actually would just be potassium oxide.
potassium oxide. Because that has a plus and the 2 minus, you cross the charge and it's K2O. There's only one way to write that. Yep. So we don't need another naming system for this. We don't need prefixes. We good?
What about the other one, C3?
C3H8? What's the prefix for 3, Aman?
Carbon,
What's the prefix for 3?
tetra,
Tri, like triangle,
triangle,
tricarbon.
monoxide.
And what 8 mean? Octa, like a octopus, right?
Yeah.
So you need to get those prefixes down. And if you want them on your little card, great, but get them down. We're going to be using them all semester long. So octa
Tricarbon,
hydride, and then water is dihydrogen monoxide.
hydrate.
We good? All right, should we see if you really understand this? All right, here we go. Write the chemical formula for that compound. Can you do this? I didn't show you how to do this yet. Can you do it? Write it down. What is the chemical formula for diphosphorus dicoxide? Or we can say decaoxide. I don't care. 2 vowels. Don't get rid of the O. So what's the chemical formula, guys? Are we good? Whether that's a real compound, I don't know. Can't remember. I could figure it out, but Questions? Okay, on the back side of this worksheet it was dealing with, on the front, on the top of it, that is some more examples of determining order of melting point, increasing melting point or boiling point. Do we remember how to do that from last time? Yeah.
Would you just determine what kind of bond, like intermolecular force?
Yeah, first step is determine intermolecular force. Whatever has the strongest intermolecular force has the highest melting point or boiling point. If they're the same, then what do we do? Yeah, check the molar mass. The atomic mass of each, add all of them up for each atom in that compound. Whatever one has the highest mass has the highest melting point or boiling point. Good? Yeah, Rebecca.
For the first example on the worksheet,
Uh-huh.
phosphorus triiodide, you write it with 2 i's.
It's what is it?
Phosphorus triiodide,
Triiodide.
iodide, sorry.
Yeah, you can't really get rid of a vowel right there, can you? Because tri, if you say tr, we don't know it's 3, right? So you have to say tri. And you can't get rid of the I on iodide because then it's odide or whatever. Who died? Somebody died. Iodide, okay? So you can't get... So here's the thing. This is a multiple choice test, right? So if you don't want to get rid of that vowel, don't worry about it. Just write it and then just choose the best answer, right? Okay. That makes sense? Any other questions? So on the bottom of this worksheet, you have more examples of writing chemical formulas for covalent compounds and naming. Yeah, Andrew.
Just for fun, what would ethanol be? I know it's organic.
What would ethanol be?
Yeah, what would the name for it?
It's called ethanol. That's not a binary ionic or covalent compound. So we're going to use the covalent system, which is ethanol.
Okay.
Yep.
There.
But if we have one carbon, it's a methyl group. 2 carbons, it's an ethyl group. 3 carbons, it's a propyl group. 4 carbons, it's a butyl group. 5 is a pentyl group. Then depending on what's hooked to that group, we give it a different name. You don't have to worry about that. That's organic chemistry. If it's an alcohol, it has OH on it. No, don't get that confused with hydroxide, because it's not. But anyway, you don't have to know it. Any other questions? That's all for this unit. Next thing we got an exam. When is the exam due? On the 23rd. I opened it. You can take it today if you'd like. Don't take it today if you're not ready. Okay? And you can't take it on Monday because that's college is closed for Juneteenth. What is Juneteenth? I don't even know what that is. Just another day to get off of school?
Yeah.
Woo! That's what I like about it. Okay. Because there wasn't Juneteenth when I was going to school. Like,
I think they
what
just
is
came out with it.
African American
Or something.
just to, because we didn't have any holidays in June, so we just need, right? Get up. Okay. I don't know. Do we have any questions regarding your study guide? I know I told you we can do it on Tuesday, but we got 2 minutes before break. If you guys want to stay longer, we can definitely go over and review and get ready for this exam, and you can take it when you're ready. Or I'll let you guys go and study and do what you need to do and have a wonderful weekend. What are you feeling? Who would like to stay and go over some stuff? Okay. Yeah, great, let's do it. Yeah. So here's the thing. Do I turn your questions down? No. If you have questions on Tuesday, bring them. If you don't, we're moving on. Fair enough?
Fair.
I think you have a lot of.
Okay? Yeah. So, yeah, if you want to ask these questions, you're not prepared today to ask these questions, great. Then you can ask them on Tuesday. But when we're done asking questions on Tuesday, we're moving on. Good? Okay, that's our break time. If you're good and don't have any questions and you got this stuff down, have a fantastic weekend. And I'll see you next week. If you have questions, I'll see you in 10 minutes. Thank you. The what? What's the best way to remember the geometry?
Yeah, the shape.
Of
Because I just don't want you to write them down because someone's not going to.
okay. I believe the geometry, since it's not the end thing, what's the end goal for the geometry? Polarity and intermolecular forces, right? So that we can understand the different properties and different solids, right? So that's why we learn that stuff. So on this test, I will test you what the electron geometry and molecular geometry is going to be. But after that, I don't think, I mean, other than the final test, it might be on the final as well, but it won't be on each other exam. So here's what did I tell you that story about that student that took it 5 times? And he passed on the last time? Well, I made a copy of that little paper and shrunk it down to this size. If you can read it, put that on there. Because for nursing, yeah, I don't think you need no geometry, do you? But it helps us to understand other things. Okay? So I would get it down if I were you, but if you, I know some of you guys' schedules are probably completely full or whatever, then you can do that. Just take a little picture of it, shrink it down. You guys can take a picture of it with your phone and put it on the computer and shrink it down, stick it on Microsoft Word and print it out, right? And just glue it on your card. Yeah, whatever you got to do. But how do I remember it? So if it's 1 or 2 regions, it's always linear, right? That's pretty straightforward. And if there's only 1 bonded atom, it's always linear. Doesn't matter if there's 4 regions or 3 regions or even 6 regions. We didn't learn about 6 regions in this class, but if there's 1 bonded atom, it's always linear as well. Okay, so you don't have to worry about those. And then, so for 3 regions, so this is domains or electron regions, right? Then you have trigonal planar, that's the main shape. How do I remember that? Because of how it is, how it's shaped. It's a triangle on the same plane. Because that's as far apart as they can be, is like that. If you try to get any further, it gets closer to the other ones, right? Okay? But what about if you bring it out like this? Oh, it's a little bit closer, right? So it's on the same plane, and it's triangular shape, trigonal planar, on the same plane. That's how I remember that one. And then if it's 2 bonded atoms and 1 lone pair, well, not that one. Then it looks like this, right? And what's that? It looks like a line that's bent. So I just try to remember, and what's causing it to bend? There's a lone pair of electrons pushing these other ones down, right? These electrons still want to be as far apart as they can, so we call this bent. Good? And then for 4, we have, what's the main shape? Tetrahedral. Tetra means 4. You guys know what a tetrahedron is? It's just a solid shape that looks like a tetrahedral. Okay, whatever. But tetra 4, hedral, just some geometric name, I guess. Okay, tetrahedral, and that looks like this, for example. They, as far apart as they can be, so that puts about 109 degrees apart, but now it's in 3-dimensional space. Okay. And then if we take one of these off and just put a lone pair right there, now what does it look like? A triangular-based pyramid. So we call that trigonal pyramid. Make sense? So that's what I kind of think about, just what does it look like? And then if we have two of them, like in water, two lone pairs, two bonded atoms, again, that's bent. And that's all of the shapes you need to know. Linear, trigonal planar, bent, tetrahedral, and trigonal pyramid. Yeah.
And then just to refresh, so for the CH3 one we read there,
Uh-huh.
so the molecular geometry would be trigonal pyramidal, but the electron geometry would be tetrahedral, right?
That's right.
Because of the lone pairs.
The electron geometry is determined by how many regions you have, right? And so the main, for 3 regions, trigonal planar is the main shape. For 4 regions, it's tetrahedral. And for 2, it's linear. And 1 is also linear. Good?
Three shape we need to know. Tetra, triangular,
Yeah, you need to know these shapes. Uh-huh.
tetrahedral.
Tetrahedral. D-R-A-L. Yeah, Andrew.
Sorry, while we're on the subject of shapes and the structures and such, in the chemistry lab class, there was one that was pretty tough.
Okay.
Because it's ionic as well as, well, it's an acetate ion.
Acetate.
Can you go through that one? Yeah.
Yeah.
Acetate.
So C2H3O.
This
2
one
minus.
says C1, or just C, H3CO2.
That's the same thing, right?
Yeah.
Same number of atoms. This is just the structure.
Okay.
So if you know it in this form, it helps you to draw the structure. But let's say we don't. Because this doesn't tell us the structure. So how do we do it? Count valence electrons, just like normal. We have 2 times 4, that's 8, right? 3 times 1, that's 3. 2 times 6 is 12. And what do we do with that? 1 more. You following? That was just a quick, okay? So we got, bring the 1 to the 3, that's a 4, plus 8, that's 12, another 12, that's 24 electrons. Yeah,
This is a polyatomic ion.
this is a polyatomic ion. Uh-huh. All right, so we have 24 electrons to use. Which one's the central atom? Carbon, hydrogen, or oxygen? Carbon, least electronegative, that's not hydrogen, right? We have 2 of them, so they're bonded together. And we have 3 hydrogens. Now where should we put them? And here's the thing. Sometimes you put it somewhere and that doesn't work. You try it somewhere else, that doesn't work. And you keep trying it until it does work. Until you get an octet on all of them and you use all the electrons. That's why this is the structure, CH3. This is the methyl group from when I talked about organic chemistry. There's the 3 hydrogens. Then you have an oxygen and another oxygen, right? How many electrons have we used so far? 2, 4, 6, 8, 10, 12. We got 12 left. Where do they go? 2, 4, 6, 8, 10, 12. Okay, great. Does this carbon have an octet? No, so we got to share. Does it matter which one you share? No, it doesn't. There you go. Now, here's a problem with this. You might come and do something like this. Right? For example, that'd be a possibility that you try. Or maybe you put an oxygen over here and an oxygen over here. Right? There's a lot of different ways you can try it. But let's see what happens. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. And we put it right there. So let's see, 1, 2. You might draw it like that, right? But that's not how it is. And yeah, I won't test you on that because this is organic chemistry. Okay?
So that was a side question is, well, I guess 2 points. I almost tried to draw it a different way because the C's were separated, like structurally.
Uh-huh.
But that doesn't mean that they're separated. It's just saying that the hydrogens are on one.
Uh-huh.
Okay.
Yep. And here's what I do. If I give you organic chemical, I will give you in structure form. If I want you to know. So for example, I might say, all right, if we have, for example, this compound right here, I might say, all right, what's the molecular geometry for that carbon? And these might be labeled, right, 1 and 2. And it might say, for carbon label number 2, what's the molecular geometry for it? Well, how many regions does it have? 3 regions. How many lone pairs around that carbon? 0. So that means, what's the molecular geometry? Trigonal planar. What is it for this one? Tetrahedral. So that could be a possible question on the test. But I won't make you draw the structure for it.
Okay.
Sound good?
And that was my other question. Is there a central carbon or central atom? Like,
There's 2 of them.
There's 2 of them. Okay.
Yep.
I didn't know if they counted as one.
Because if we draw this 3-dimensionally, it would look something like this. And then we can draw that's what it would look like. Good? Again, I'm not going to have you draw that. That's
It's not bipolar, right?
yes, what makes it polar? That part right there. Yep. Because these are non-polar bonds, right? Yep, that's right. Uh-huh.
And then, 2 questions. What would be the shape of the CO2 that's bent, right?
So this is not CO2. It's right there.
Oh, that shape, okay. That's trigonal planar.
Yeah, uh-huh.
Oh, right.
Carbon is always the central.
Yeah, if there's carbon in it, it's always essential.
Is the main element.
And there has to be either 4 bonded atoms or 2 double bonds or 1 double bond and 3 bonded atoms.
It's
right.
organic chemistry.
Or 2 bonded atoms, I mean, yeah.
And for polyatomic ions, we put it in the bracket and leave the charge
Uh-huh.
just for polyatomic ions?
Yep.
But that doesn't mean that that negative is like representing electrons that we didn't count in the Lewis
It means it gained an electron. That's what that negative means.
But didn't we add that electron to the Lewis structure?
Yeah, because it gained one.
So it's just representing that. It's not
Yep.
like
It represents, and where's that negative? It's around this oxygen. You don't need to know that for this class, but that's where it's at. And then what happens? This guy comes over here and hooks up with it. That's organic chemistry. You don't need to know that. Yeah.
I don't know if it's possible, but what will happen if there's 2 elements that have the same electronegativity? Like, what will be the central one?
So like carbon and sulfur, for example,
Yeah.
then it would be CS4. I would go with the one that's all alone. All by itself. There's no other one,
Well,
right?
for example, if there's for example, acetate, there's like various
Uh-huh.
elements. Which one will be the central one?
Carbon. Because hydrogen's never the essential atom. Do you understand why?
Yeah, no. My question is, for example, I don't know if it's possible, like carbon, sulfur, hydrogen, and oxygen. Which one will be the and carbon have the same electronegativity?
You won't have to worry about that.
Okay, I'm just curious because
But if that was a compound, I'd go with carbon every time. If it has carbon in it, that's going to be the central atom every single time. So carbon is that one in group 4, and those guys are kind of a little weirdos, right? So those guys you need 4. Thanks.
Thank you.
Good? Any other questions?
So this carbon is always in organic chemistry.
Yes, that's what organic chemistry is carbon chemistry.
Have not been,
Well, we deal with carbon as well.
but in organic chemistry.
We deal with it in this class too.
Yeah.
We just don't do big, huge compounds in this class. Well, you can ask. You can ask right now if you want. Any other questions? Yeah, Chad.
Could you do number 6 on the study guide?
Yeah.
Know how to write the chemical formula and name the ionic compounds with polyatomic ions.
Yeah, so for example, if we have Na2SO4, or we call it sodium sulfate. So know how to write the chemical formula. So if you're given sodium sulfate, well, sodium is Na plus, right, on the periodic table. And sulfate is SO4 2 minus. Then you cross the charges and we get this.
Okay.
Or if you have to name it, how do we name the cation? If it's a main group element, we name it element name. If it's a transition metal, we use element name plus the Roman numeral, right? So we use those rules to name it. And polyatomic ion, we just use the name of this polyatomic ion.
Followed by the, like if it was a compound with a polyatomic ion and another ion, how would you name that?
So like
How would it be this?
NH4OH, that's 2 polyatomic ions. We name this one as a polyatomic ion. We name this one as a polyatomic ion. Yep, ammonium hydroxide. Yep.
And then number 10, know which compounds dissociate in water.
Yeah, we talked about that today. Which compounds? What are salts called? Ionic compounds.
So all of those dissociate in water.
Well, no, but for this exam, yes. We'll get into it in another exam. Great. Anything else? Okay. Study, study, study. I mean, if you have more questions right now, we can just, because I'm here till 4:30 anyway, so. And this class doesn't end till 12:30, so. Thank you. Take care. Did you have a question, Mon? Thanks, Emma.
Question number
24?
24. Know why an compound dissolves in each other or not?
Okay, so we talked about like dissolves like, right? This is how you know whether it does or doesn't dissolve. And what I mean by that, tell me when you're ready. So like dissolves like means polar substances will dissolve in other polar substances. Non-polar substance will dissolve in non-polar substances. Yeah. Yeah, like dissolves like. Yep. And that's how we figured out soap will get oil out of stuff if you mix it with water. You ever try getting oil off of a pan with water? Doesn't work. Uh-huh. And non-polar dissolves in non-polar. Thanks, Erica. Yeah. Thanks, Sarah. Take care. Oh. Yeah, thank you. Take care, Ken. Hey, can I grab this real quick? Can I? Sorry, I just. Hello. Hey. How you doing, Ollie? Oh, sorry about that.
We did it in,
Uh-huh.
I haven't even done the data sheet, so.
Yeah. Oh, heck yeah. Perfect. Uh-huh. Oh, nice.
So this is the post letter. I mean, you can just look at it. Okay, I got 1.75. You can just do it right now. If that's okay. Yeah.
Okay. So my wife will probably be there. I'll let her know. And then.
It was so annoying because I double checked myself and I still.
Okay, good. So, can she pay credit card or cash? What do you mean?
Oh, did you guys have to do a ride?
Okay.
Okay.
I don't think you did, it's just yours, yeah. But it's probably good because
Okay.
I haven't tracked.
All right. I'll let her know. Okay, thank you. All right, appreciate it. Okay, bye. All right, sorry about that. That's not professional.
Last time, Tuesday, and online, there's only 1 hour.
I know. I apologize, but for this class, I did write on there that if you go down, because all my old ones are down there, and I told you which one to go to. I think it was covalent compounds part 2. I think don't go by my word, but I wrote on canvas which one you go to down below. Yes, I'm sorry about that. I just forgot to push pause after the break or push record again. And
Just question number 8, know all the polyatomic name lines.
uh-huh.
Can you tell me a couple examples?
Yeah, I gave you a whole list of them. Do you have that list?
Yes.
That's the one you need. You need to know. In fact, was it last time? Oh, here it is. Oh, no. Do you have that page? Ah, I took it out. I don't have it in here. Yeah, you need to know those.
So I can say, know all palatine, like,
There's a shorter list online if you want on my notes.
one of them is
Do you have the notes here?
the printed.
Yeah, the printed notes, because they're on here.
I printed
So go back over here.
molecular shape.
Yeah. Sorry, I don't mean to touch you. Keep going.
I'm not like a girl speaking.
What?
I'm not like a girl speaking. So, nomenclature,
Yeah, keep going. Almost, right there. That's a smaller list. If you want to memorize those, that's great.
we can also take it on notes on our small note.
Yeah, you can write whatever you want, but we need to know this for the rest of the semester. So eventually make sure you get it down. Thanks, take care.